Hello everyone, I will introduce the paper Integrating Multimodal Electronic Health Records for Disease Prediction. First, I will introduce EHR data. An electronic health record is a digital version of a patient's paper chart. It provides a long-term view of a patient's health, including their demographics, diagnosis information, and clinical features. For example, this record shows that the patient has 3 hospital visits. For every visit, the corresponding information is recorded. Here, the diagnosis information is recorded with ICD-9 codes, and the clinical features include vital signs and lab test results, which contain plenty of details about the patient's symptoms. Next, we introduce the characteristics of diagnosis codes and clinical features. Diagnosis codes can be classified into a smaller number of clinically meaningful categories according to the disease taxonomy. The disease taxonomy contains the hierarchy of disease concepts in the form of a parent-child relationship. Here, Figure 1 is a toy example of disease taxonomy. Lymph nodes, or solid circles, represent diagnosis codes, while non-lymph nodes, or dashed circles, represent more general concepts. Clinical features contains vital signs and lab test results, and it has irregular temporary interval between observations and different sampling rates between sequences. For example, Figure B shows the observation time steps of a subset of features for one patient in the MIMIC3 dataset. Black lines indicate observation time steps, whose number and timing vary across patients. Then, we introduce the diagnosis prediction task and existing works. Given the patient's historical information, the goal of disease prediction is to predict diagnosis codes in the next visit. Most existing works utilize the disease taxonomy to learn the diagnosis code embedding, and then for every visit, they learn diagnosis code representation and feed the representation into sequential models and perform prediction tasks. However, the limitations of previous works are very obvious. Firstly, most methods only use medical codes as input and ignore other useful information such as clinical features and demographics. But clinical features can be considered as a significant complement of diagnosis codes. Similarly, patient demographics record the static information about the patient. Combining clinical features and demographics with diagnosis codes can greatly boost the prediction performance. Secondly, even if some works integrate the clinical features into the diagnosis prediction task, they ignore the fact that the importance of clinical features varies enormously for different diseases. Based on the above limitations and the characteristics of clinical features, we propose a multimodal diagnosis prediction framework, which contains the clinical feature weight adjustment mechanism and the attentive clinical feature aggregation mechanism. Our model uses 3 kinds of information as input, including the diagnosis code information, demographics, and clinical features. Our framework mainly contains two parts: diagnosis code encoder and clinical feature encoder. Next, we describe the two parts separately and show how they can be optimized jointly. For the diagnosis code encoder, given the disease taxonomy, we first obtain the diagnosis code embedding matrix M, where each column is the embedding of the corresponding diagnosis code. For the test visit, given the diagnosis information xt, we first compute the vector vt using this equation. Then we feed vt into GRU and use the hidden state ht to denote the diagnosis code representation. For clinical feature encoder, we first transform the clinical feature CT with a linear layer to obtain CT prime, and then we feed CT prime into the clinical GRU alpha to obtain the hidden state GT. Then we compute a vector K that contains the diagnosis code representation HT and the demographic information P prime, and we adjust the weight of the clinical features based on vector K. After the weight adjustment part, we could obtain the clinical features CT omega, and then we input CT omega to the clinical GRU beta. Here, this clinical GRU beta serves as the attentive clinical feature aggregation mechanism. We assign different weights to different time steps and use the weighted sum of the hidden state as the final representation of the clinical features. After we obtain the diagnosis code representation and clinical feature representation, we can calculate HT, which is the diagnosis code representation, the demographic representation P prime, and the clinical feature representation QT prime as the overall patient's health status. And then we perform the prediction task. The overall loss function is listed here. Next, we introduce the experiment. We use MIMIC3 dataset, and the diagnosis code, demographic information, and clinical data and clinical features are used as input. We use recall and MAP as evaluation metric. MAP refers to mean average precision. We select 7 baselines and split them into 3 groups. Methods in Group 1 do not use the disease taxonomy information. Methods in Group 2 use the disease taxonomy information, and the inputs are the patient's diagnosis codes. Methods in Group 3 use the multimodal data as input. This table shows the performance comparison. It shows that our proposed model, MDP, outperforms all the baselines and achieves 1.2% higher for recall at 20 and MAP at 20 over the best baseline. Then we analyze the clinical feature importance. The clinical feature importance is calculated by the absolute value of beta times alpha, and we can calculate omega I at all time steps to obtain the importance matrix. Here, We give examples of 2 patients. This table shows the diagnosis codes of the 2 patients in one hospital visit. The 2 figures show the heat map of the clinical feature importance matrix for these 2 patients. The x-axis is the clinical feature, and the y-axis is the time step. The color represents the feature importance. The darker color means the more feature importance. It shows that clinical feature weight adjustment mechanism can adjust the weights of clinical features based on the patient's health condition. Meanwhile, clinical features in the later time steps are assigned more weights because they are more helpful to predict the diagnosis codes in the next visit. Then, we show the correctly predicted diagnosis codes of other 2 patients in the top 20 predictions. For patient 1, the ground truth contains 14 diagnosis codes. Our proposed model correctly predicts 7, while other baselines mainly correctly predict 4 to 5. And our proposed model could predict V45.82. This describes the details of the diagnosis. Patient 2 has similar observations. Here is the conclusion. In this paper, we propose a novel and effective deep learning framework which uses multimodal data for diagnosis prediction. We design a clinical feature weight adjustment mechanism which learns the correlation between the patient's diagnosis codes and the clinical features, and adjust the weight of clinical features based on the patient's health condition and demographics. We incorporate an attentive clinical feature aggregation mechanism into the framework to deal with the missing data and the varying time granularity of clinical features. Thank you. That's all.